Hello guys and gals, and welcome to part 2 for section 5.9. And in this part, we're going to look at how we actually use the steady state approximation to solve for the overall rate law of a reaction, if all that we're given is the reaction mechanism. Okay? Now, normally, if we're given a reaction mechanism and everything's irreversible and the first step is rate limiting, we can literally just find the rate law of the slowest step and we can call it a day. But when we have equilibrium, or when the first step is not the rate limiting step, we have to use the steady state approximation, which allows us to find the rate of the intermediates and use those to solve for the overall reaction order. Now I know that I've written it a little differently in your notes for this example problem, but I'm going to explain it in a different order of what is written here. So first things first, we have been given the overall equation and asked to find the rate law for the reaction. And then the only thing they gave us was the three-step mechanism. Now, notice that in the three-step mechanism, immediately you can see an equilibrium sign. That means we're going to have to use steady state approximation. And I point that out because on the AP exam, most of the time, they will actually tell you still which of these steps is slow and which of these steps are fast. But that is not going to allow you to just find the rate law of the slow step and be done. So let's talk about why. Now, in this case, they haven't told us. So let's see if we can figure out which of these steps should be the rate limiting step. Let's see if we can infer or hypothesize. Now, step 1 cannot give us the rate law for the overall reaction because it is at equilibrium. Okay, so because the reactants in this case are also products and the products are also reactants, it's not going to be able to give us the rate law for the overall reaction. So it can't be step 1. Step 2 and step 3, well, let's see. They both produce some products of the overall reaction. Step 2 produces nitrogen dioxide and oxygen, while step 3 only produces nitrogen dioxide. And step 2 also produces one of the intermediates. We can see nitrogen monoxide being produced in step 2 and used up in step 3, making it an intermediate. So because step 2 makes more of the products of the overall reaction and one of the intermediates needed for the reaction mechanism, step 2 is probably going to be our slowest step. Okay? Step 2 is probably going to be our slowest step. And like I said, they will tell you that on the AP exam still, but I just wanted to go through it in this kind of situation. So, if step 2 is our rate determining step, okay, well, it's an elementary reaction, meaning that we can just take the coefficients as the orders of each reactant, and we should be able to be done. So let's write the rate law for this overall reaction. First, let's put the overall reaction down. We have 2 into O5 produces 4 moles of nitrogen dioxide and 1 mole of oxygen, okay? So the rate law for this overall equation should have N2O5 involved in it somewhere because N2O5 is the reactant. But the rate law for step 2, if it were being used for the overall reaction, is this. We have an intermediate in this rate law, and we have a product in this rate law. This rate law cannot be correct for that overall reaction. Okay, it's not. And it is because the first step is in equilibrium, and that first step is not rate determining. So we need to use our intermediates to determine what the real rate law is. Now we're going to keep this one up here because it might be useful to us later on. But right now, let's go back and let's figure out what our intermediates are. Now I already told you that NO3 is an intermediate, and NO3 is an intermediate because it's produced in step 1 by this reaction, but then it is consumed in steps 1, 2, and 3. So it's produced by the forward reaction in step 1, but it's consumed by the reverse reaction in step 1, and then it is a reactant in steps 2 and 3. So because it is produced by the reaction and used up by the reaction, it's an intermediate. I also pointed out that NO is also another intermediate. So we have two intermediates in this case. Now, in order to use the steady state approximation says that intermediates are produced just as fast as they are consumed. So we need to find the rate law for how quickly each of these intermediates was produced, and then we need to find the rate law for how quickly they were consumed. And we'll be able to use that information to help us solve for the actual overall rate law. So let's start with NO3. So we'll start with the rate of appearance. What is the rate law for the rate of appearance of NO3? Well, there's only one place that NO3 is produced, and it's in step 1. So the rate law for this elementary reaction would just be R is equal to K1, because the K value of each of the steps is different than the overall K value, okay? So K1 times N2O5 to the first. And that's it. That is the rate law for the production of NO3. So now let's find the rate law for the rate of disappearance of NO3. And this is going to be a little more difficult because NO3 is consumed in 3 steps. It is consumed in 3 different steps. So we need to have 3 different rate laws because each of these steps contributes to NO3 being consumed, to it disappearing. Okay? Step 1, it is consumed in the reverse reaction. And I know we're not used to looking at a reaction this way, but keep in mind that step 1 is in equilibrium. So our products are also our reactants. Okay? So for this, I'm going to say the rate of disappearance for step 1 is going to be R is equal to KR. I'm going to use that for reverse, so that way we know we're not talking about the forward reaction in step 1. We're talking about the reverse reaction in step 1. And it's going to be times the concentration of NO3 times the concentration of the other reactant in the reverse reaction is NO2, and they're both to the first order. Okay? For step 2, when it's produced, we'll have R is equal to K2, and that will just be our 2 reactants to the first order since both of their coefficients are 1. So, again, we'll have NO3 and NO2, just with a different K value. Finally, in step 3, we'll have R is equal to K3, and that one is NO3 times NO. If we go back and look at the reaction mechanism, we can see that the reactants for step 3 are NO3 and NO. The next piece of this, of the steady state approximation, is to set each of these rates equal to each other, because the rate of appearance is equal to the rate of disappearance. So let's write these out so that they're equal to each other. Okay, so instead of saying R equals these things, I'm just going to say K1 times the concentration of N2O5 is equal to each of these rates of disappearance. And I'm just going to add those rates of disappearance together because they all contribute to the disappearance of NO3. So we'll have KR NO3 NO2 plus K2 NO3 NO2 plus K3 NO3 NO2. All right, so we have done the first piece of the steady state approximation. We determined which step should give us the rate law, and we saw that that rate law could not be correct for the overall reaction. So we determined our intermediates. We found the rate of appearance of one of them and the rates of disappearance of one of them, and we set them equal to each other. And this is where we will